In our most recent sequences, we looked at frequency domain analysis of circuits. We saw that we could plot the behavior of the circuit as a function of the input frequency. Okay, and this kind of analysis was called sinusoidal steady state analysis, where we looked at the steady state behavior of the circuit when sinusoids were input. Today we're going to close the loop, so to speak, on this topic and compare both frequency domain analysis with time domain analysis. Okay, so in the beginning we had looked at time domain analysis, and then we looked at frequency domain analysis. We will try to bring both of these things together in this lecture and just make sure that we all understand how the two relate to each other. The readings are section 13.6.3 and pages 819 through 823 of the textbook. So let me start with a quick review before we go into comparing time domain versus frequency domain analysis. So when we looked at time domain analysis in the past, we looked at input signals of the form Vi, small v, capital I. We had some kind of a voltage source, and the voltage could have been a step or an impulse or other such things. And we input voltages like this or signals like this to some systems. Okay, and the system could be, for example, an amplifier. Okay, an amplifier. And then we obtained some output. Okay, in this case the output may have been some V0. And the amplifier would, in this example, would amplify the input signal and we would get the output. And this was a time domain form of analysis, and we had input time domain input signals and time domain output signals. In the most recent sequences, we looked at a different kind of view of the world. Okay, and this view of the world is the filter view of the world. So in this view, what we said was we can build these boxes, these systems, okay, called filters. Okay, and a filter, for example, might be a low-pass filter, or the filter could be a band-pass filter, such as you saw in the AM tuner example. Then what we said was we would apply input signals, and in this case, the input signals were represented by their complex amplitudes. Okay, so as an example, I could have a Vin signal, and this would be the real or complex amplitude of a sinusoid. So the example input signal might look something like cosine Vn cosine of omega t. And what the filter would do is the filter would process the signal and produce some output. And in this case, the output would be Vout. And Vout again would be the complex amplitude. Okay, where the time domain function, so in this case, the input time domain function was Vin cosine omega t. And here, the time domain output function written like this would be represented by something like this. Okay, would be the magnitude of the complex amplitude, cosine omega t, plus the phase of the complex amplitude. But in shorthand notation, we represented such systems as filters, where the filters took in these amplitudes as input, these complex or real amplitudes of sinusoids as input, and produced some complex amplitude as the output. Okay, this was a filter view of the world. And what the filters did was process the input according to frequency. So if I had a low-pass filter, the transfer function of the low-pass filter might look something like this. Okay, so this might be Vout divided by Vin magnitude, okay, as a function of omega. And these filters would look at the frequencies coming in and process the frequencies according to their transfer function. Okay, this is the filter view of the world. And then we looked at a whole bunch of filters. Okay, so let's draw the bunch of filters that we looked at. Okay, so for instance, in each case, I'm looking at the magnitude here. There's also the phase associated with it. I'll just look at the magnitude for now. So I could have a transfer function that looked like this. Okay, this is an example of a low pass filter. I could have another example with again Vout divided by Vn, and in this case I could have a transfer function that looked like this. This would be a band pass filter. Another example would be something like this, would be something like this. This would be a high pass filter. Okay, there are other examples. So we saw one more example, and that example looked like this. Okay, and this was a band stop filter. Okay, band stop filter. In this kind of a filter, it would let through everything except for the signals in a given frequency range. This was called a band stop filter. Okay, we also call this a notch filter. And as I mentioned to you earlier, getting perfect filters like this, okay, like in this band pass filter, is extremely difficult. And what we end up getting in real life is something that looks like this, may end up looking something like this, okay? And sophisticated filter design would try to make these edges come as close to a rectangular transfer function as possible. All right, now we then looked at the following RLC circuit. And in this RLC circuit, we looked at an input VI, which was a sinusoid of the form VI cosine omega t, where VI given here is the real amplitude of the sinusoid. And then this is a very, very interesting circuit. Okay, depending on where you take the output of this circuit, you actually get very different kinds of filters. So as one example, we spent quite a bit of time on the output taken across the capacitor, okay, at VC. So for that kind of a circuit, you recall the output looked like this. Okay, you recall for VC, so here I'm plotting VC divided by VI, the magnitude of that. And we saw that the output looked something like this. Okay, this was omega naught, where omega naught was 1 divided by square root of LC. We saw that under certain conditions the output would have looked like this. Okay, recall the way we got that very quickly was looked at extreme case behavior of the circuit. So for example, for very low frequencies, okay, for very low frequencies, the capacitor would behave like an open circuit, and so therefore the input would fall pretty much across the capacitor. However, for very high frequencies, the capacitor would behave like a short circuit, and so there would be very little drop across the capacitor, and therefore the voltage would be pretty low. So this is for high omega. Then we also said, so in this case, C was open to low omega, and here C was short to high values of the frequency. Then we also said that for high Q circuits, okay, when Q for the circuit was very low, we said that the circuit would have a peaky response that looked like this. Okay, so where this value was given by Q. So if the Q was large, then the circuit would have a very peaky response where the output taken at VC, the complex amplitude, could be substantially greater than the input amplitude. Okay, this made for very, very interesting circuits. So this is whether it's a high Q filter, so this would be a high Q filter, and down here we have a, I guess we have a not so much of a high Q filter. Okay, it's a low Q filter, although we don't quite say that. Okay, so depending on where I take the input of the circuit, I actually can get different kinds of filters. Now this filter, the green filter here, is an example of a low pass filter. Okay, the reason taking the voltage across the capacitor gave me a low pass filter was the capacitor behaved like an open circuit to low frequencies, and so therefore it is a low pass filter. I can also build other kinds of filters from this very circuit. So another example of a filter that I can build is by taking the output across the resistor. Okay, so say for example, if I take the output across the resistor VR and plot the magnitude of the transfer function at VR, then we also saw that we got a function that looked like this. Okay, and this was an example of a band pass filter. And the reason the circuit behaved like this was, recall, when the frequency approached omega naught, then at that frequency the impedance of the inductor and that of the capacitor tended to cancel each other out, causing the signal to drop pretty much across the resistor. Okay, and for very high frequencies, for very, very high frequencies, the inductor L was open. Okay, so most of the voltage fell across L. For very, very low frequencies, C was mostly open. Okay, so most of the voltage fell across C. So that's the band pass filter. Okay, now, well, there's one more place that I could take the output, and I could take the output across the inductor L. So I would like you to hit the pause button on me. Okay, I would like you to hit the pause button on me and figure out for yourselves what you might expect the voltage across the inductor to look like. What kind of a filter might you get?